For most of human history, Neptune was completely invisible to the naked eye. Unlike the bright planets that have fascinated civilizations for thousands of years, this distant world remained hidden in the darkness beyond Saturn and Uranus. In fact, Neptune became the first planet discovered through mathematics before it was ever seen through a telescope. During the early 19th century, astronomers noticed something unusual. Uranus was not moving exactly as predicted. Tiny irregularities in its orbit suggested that an unseen object's gravity was pulling on it. Instead of dismissing the discrepancy, mathematicians calculated where this mysterious planet should be. When telescopes were pointed toward the predicted location, they found Neptune almost exactly where the calculations had placed it. It was one of the greatest triumphs in the history of astronomy. Yet discovering Neptune was only the beginning. More than 4 billion kilometers from the Sun, Neptune receives less than 1,000th of the sunlight that reaches Earth. 1 year on Neptune lasts about 165 Earth years, meaning humanity has never observed the planet complete a full orbit since its discovery in 1846. Its immense distance has made Neptune one of the least explored major planets in our solar system. Even today, only one spacecraft has ever visited it. In 1989, Voyager 2 flew past Neptune, capturing breathtaking images of a deep blue world unlike anything scientists had expected. Instead of a frozen, inactive planet, Voyager revealed enormous storm systems, clouds racing through the atmosphere, and winds exceeding 2,000 km per hour, making them among the fastest measured anywhere in the solar system. That discovery immediately raised an important question. Why is a planet receiving so little sunlight so incredibly active? Scientists believe the answer lies beneath the clouds. Neptune releases significantly more energy than it receives from the Sun. Some of that heat appears to escape from deep inside the planet, fueling powerful convection currents that drive its remarkable weather. Warm material rises through the atmosphere while cooler gases sink, creating a constantly changing system of storms and high-speed winds. Its neighboring planet, Uranus, presents a striking contrast. Although Uranus and Neptune are similar in size and composition, Uranus appears comparatively calm. Neptune, meanwhile, remains dynamic and turbulent, suggesting that important differences exist deep within their interiors. Exactly why those differences exist remains one of planetary science's biggest mysteries. More than 3 decades after Voyager's historic flyby, a new generation of observations began with the James Webb Space Telescope. Unlike visible light telescopes, Webb specializes in infrared observations, allowing scientists to study heat, atmospheric chemistry, and cloud structures with remarkable sensitivity. Instead of simply taking sharper pictures, Webb examines how different molecules absorb and emit infrared light. This gives researchers new ways to investigate temperatures, atmospheric composition, and physical processes occurring high above Neptune's cloud tops. One of Webb's most intriguing discoveries involves Neptune's auroras. On Earth, auroras appear near the polar regions when charged particles from the Sun follow Earth's magnetic field into the upper atmosphere, producing the familiar curtains of glowing light. Neptune, however, is far more complicated. Its magnetic field is unusually tilted relative to the planet's rotation axis and is also significantly offset from the planet's center. Because of this unusual geometry, incoming charged particles do not always follow the simple paths seen on Earth. Recent observations suggest that Neptune's auroral emissions can appear away from the traditional polar regions, indicating that the planet's magnetic environment behaves in ways scientists are still working to understand. This alone would make Neptune a fascinating object of study. But another observation proved even more surprising. Comparisons with earlier measurements indicate that Neptune's upper atmosphere appears substantially cooler than it was during the era of Voyager 2. For a world that changes slowly over decades, this is an important result. The upper atmosphere is influenced by several competing factors, including energy from the sun, heat rising from the planet's interior, atmospheric circulation, and complex chemical interactions. If temperatures are changing, then one, or perhaps several, of these processes may be evolving in ways that current models do not fully explain. Researchers are now trying to determine whether this cooling represents part of a long-term seasonal cycle, changes in atmospheric circulation, or another process that has not yet been fully identified. At the same time, Neptune continues to display active auroral behavior, adding another layer of complexity to an already mysterious planet. Rather than solving Neptune's mysteries, the James Webb Space Telescope has revealed just how much remains unknown. And as scientists continue studying this distant ice giant, they are beginning to realize that the greatest surprises may not lie within its atmosphere alone, but also among the remarkable worlds that orbit it. The James Webb Space Telescope has revealed that Neptune is far more dynamic than once believed, but its atmosphere is only part of the story. Surrounding this distant ice giant is a collection of moons, rings, and magnetic interactions that continue to challenge astronomers and reshape our understanding of the outer solar system. One of the biggest puzzles is Neptune's weather. Unlike Earth, where sunlight powers most atmospheric activity, Neptune receives only a tiny fraction of the Sun's energy. Despite this, the planet remains remarkably active. Massive storms appear, evolve, and disappear over time, while clouds form at different altitudes and are carried across the atmosphere by extraordinarily powerful winds. Some storms are so large they could easily engulf Earth. When Voyager 2 visited Neptune in 1989, it photographed the famous Great Dark Spot, a giant storm similar in appearance to Jupiter's Great Red Spot. But when astronomers later searched for it using the Hubble Space Telescope, it had vanished completely. Instead of being permanent, Neptune's storms seem to be temporary features that can form and disappear over surprisingly short periods. This tells scientists that the atmosphere is constantly changing. Another mystery lies deep beneath the visible clouds. Measurements show that Neptune radiates more internal heat than scientists expected. That hidden energy is believed to power the planet's violent weather, yet researchers still do not fully understand where the heat comes from or why Neptune releases much more energy than its neighboring ice giant, Uranus. If both planets formed under similar conditions, why do they behave so differently today? That question remains unanswered. Recent infrared observations from the James Webb Space Telescope are helping scientists investigate how heat moves through Neptune's atmosphere. By studying different wavelengths of infrared light, researchers can map temperature variations and identify gases that reveal how the atmosphere circulates over time. Each observation provides another clue, but no complete solution. Beyond the atmosphere lies one of Neptune's most fascinating companions, Triton. Unlike most large moons, Triton does not orbit in the same direction that Neptune rotates. Instead, it travels in a retrograde orbit, moving opposite to the planet's rotation. This unusual motion strongly suggests that Triton did not form alongside Neptune. Scientists believe it was once an independent object in the Kuiper Belt, a distant region beyond Neptune filled with icy bodies left over from the formation of the solar system. At some point in the distant past, Neptune's gravity captured Triton, permanently changing both worlds. That dramatic event may also explain why Neptune's original moon system appears so unusual today. Triton itself is extraordinary. Although its surface temperature is among the coldest measured anywhere in the solar system, Voyager 2 observed dark plumes rising above its frozen landscape. These geyser-like eruptions indicated that the Moon is not geologically inactive. Instead, heat from its interior may still be driving icy volcanic activity known as cryovolcanism. Some planetary scientists also suspect that a layer of liquid water mixed with ammonia could exist beneath Triton's frozen crust. If such an underground ocean exists, Triton would join a growing list of icy worlds that may contain hidden reservoirs of liquid beneath thick shells of ice. These possibilities make Triton one of the most scientifically important moons in the outer solar system. Together, Neptune and Triton form a planetary system unlike any other. One is an active ice giant powered by mysterious internal heat. The other is a captured world that may still be geologically alive despite its immense distance from the Sun. The James Webb Space Telescope has begun adding remarkable new detail to this picture, but every answer seems to reveal another unanswered question. How does Neptune generate its powerful winds? Why has its upper atmosphere cooled over recent decades? How exactly does its unusual magnetic field shape auroras? What drives its internal heat? And what secrets remain hidden beneath Triton's frozen surface? These are not signs that planetary science is failing. They are reminders that exploration is an ongoing process. Every generation builds upon the discoveries of the last, replacing assumptions with better observations and more accurate models. Neptune was once known only as a mathematical prediction. Today, it has become one of the most complex and scientifically valuable worlds in our solar system. With powerful observatories like the James Webb Space Telescope continuing to study the distant frontier, astronomers expect many more discoveries in the years ahead. The farther we look into the darkness beyond the giant planets, the clearer one truth becomes. Neptune is not simply the last major planet before interstellar space. It is a dynamic, evolving world that still holds some of the solar system's greatest mysteries, waiting for the next generation of explorers to uncover.